Many people are confused about how to find the binding energy before and after a nuclear change in order to compare them. So this is an example of a fission equation. This is part of the Learning Target 6 Chemistry Notebook Reflection. And you are supposed to look up and compare the average binding energy of the uranium-235 that's undergoing fission and compare it to the average binding energy of the bromine-87 and lanthanum-146. So the way that you do that is you go to the photographic periodic table of the elements. It looks like this, periodictable.com. There are lots of online periodic tables. So once you get to the photographic periodic table, you should bookmark it. You can bookmark it by simply hitting the star and then hitting save. So we're going to go to uranium-235. Here is uranium right here, number 92. We're going to click on it. And then there's lots of information on this element page about uranium, but we want to look at its isotope data. So we're going to click on the uranium isotope data link. And then we want to know about uranium-235 and what it has for binding energy. So we're going to click on it. And then you can see here the half-life information and then all kinds of information over here about uranium-235. But here is the binding energy, 7.591. Let's round that to the thousandths place. So 7.591 is the binding energy of that uranium isotope. So that's the amount of energy it takes to hold its nucleus together. And so you would write that down, 7.591. And then you would go and find bromine-87 and lanthanum-146. And then average them together. So bromine is here. And it's bromine-87. So we click on that isotope. It has a binding energy of 8.606. And then the last one is lanthanum-146. And that has a binding energy of 8.378. So if we average the binding energy of lanthanum, oh sorry, that's the wrong one. There we go, 146. So 8.239 is the binding energy for lanthanum. So it sounds like we have the binding energy for uranium is about 7.951. Bromine is about 8.6. Lanthanum is about 8.4. So about 8.5. So we're looking at an increase in binding energy from about 7.5 to about 8.5. Those are just approximations. I would like you to write down the real binding energy numbers to the thousandths place. If you have two elements on one side of the arrow like this, I would like you to average their binding energies so that you have an average binding energy for your starting material in the equation and an average binding energy for the ending or the daughter atoms. And then you can see if there has been an increase or a decrease in binding energy. In most nuclear reactions, there is an increase in binding energy because the reason that the atoms are undergoing radioactive decay or fission or fusion is to become more stable. And the nucleus is more stable when it has a higher binding energy. So you should expect to see the average binding energy of the daughter atoms to be higher than the binding energy of the parents. And that's it. That's how you compare the binding energy before and after for these three different nuclear changes. Again, it's the photographic periodic table of the elements where you can find that information, and you look for the isotope data link at the top of the element page.